Alright, so in this chapter what we're going to do is we're going to change our area of studying. Up to this point in time we've only been studying translational motion, which means that we've only been looking at how an object moves over time based on treating it like it's a spherical cow or one point in space, and then we track that point as it is displaced in space and how it's displaced. We've studied the kinematics, we've studied the dynamics, which is all of the forces, and we've studied the energy and momentum and the conservation quantities that are associated with translational motion. But now we're going to be looking at rotational motion, and we're going to do the exact same thing for rotational motion that we did for translational motion, which means that we're going to look at the kinematics of rotational motion. Then we're going to look at the dynamics of rotational motion, and instead of forces we study torque. Forces are for translational motion, torque is the equivalent for rotational motion. We're also going to be looking at rotational kinetic energy and rotational or angular momentum for an object that's rotating. So what we're going to do is we're going to use translational motion and everything that we know about each of these topics for translational motion, and we're going to find its equivalent or how it works for rotational motion. And in that sense, we're going to be able to take what we know about how objects move in the spherical cow model, and we're going to be able to describe any object that rotates in just as much detail. In order to do that, we need to know what a rigid object is, because in translational motion we pretended like every single object was a spherical cow. Now in rotational motion we're going to pretend that every single object is rigid. So a rigid object is just an object with a definite shape that doesn't change where the particles are in a fixed position compared to each other. So the neat thing about that is that a rigid shape is more or less the easiest to describe. It's like a perfect shape. A rigid shape doesn't compress, it doesn't squish, and inside of it, if we've got one particle inside of a rigid shape, so we'll take this as a rigid shape. If you've got a particle in a rigid shape, that particle is going to stay right there the whole time as the rigid shape moves, and all of the particles stay in their place as a rigid shape moves. So real objects aren't rigid. They can vibrate, they can squish, they can deform when a force is exerted on them, but most of the time the effects of squishable vibrating objects are really small, and we're going to be able to consider the overall shape of an object as still a good approximation, just like we were able to treat the spherical cow as a good approximation of translational motion. So the first thing that we're going to do is we're going to establish what are our quantities, or with what values do we measure rotational motion. And in order to do that, we're going to establish what rotational motion is. So translational motion was the motion of an object based on its center of mass in the spherical cow. Alright, so a spherical cow would be treated like a center of mass, and we'd just watch how it changed in a direction over time. Rotational motion is rotation around an object's center of mass. So now we're looking at inside of it, a particle, and how that particle moves over time around a certain point. And so I said around an object's center of mass. That's not always the case. The around that we really want to focus on is we want to focus on around the axis of rotation. The axis of rotation is always perpendicular to the circular motion, and it's always the center of the circular motion. So let's go ahead and let's observe this particle. This particle, the entire time that it's moving, is moving around the toothpick. Alright, that makes the toothpick the axis of rotation. It's at a 90-degree angle, and it's the point at which the whole object moves around. So that's your axis of rotation. Every point for rotational motion moves in a circle whose center is on the axis of rotation, and we call that distance between any point that moves around and the distance to the axis of rotation, we call that the radius. And that will always be the case. The radius doesn't have to be at the center of an object. I could have put the toothpick in a different position, and the motion still would have been around that point, and so the radius still would have been from the point to that object, to the center. So what we do is when we measure in translational, we measure meters of disposition. When we measure for circular motion, we're going to be measuring radians. And so let's see how that works. So you've got this point P on an object that rotates around the center of axis of rotation. If we take point P and we rotate it upward, all right, it will cover an arc length L. And remember, it has a radius R. And you know that if it does that, it will cover a displacement theta. And so that theta is how we're going to measure how far an object moves around a circle, because it can do it 360 degrees, it can do it 720 degrees, so on and so forth. But we're not going to be using degrees. Instead, we're going to be using radians. So every time you see theta, that tells us how far an object is rotated or moved about its axis, and the measurement is in radians. If you're not familiar with radians, you know that 1 radian is going to be equal to that arc length divided by radius when the length and the radius are equal to each other. So to calculate any value, any theta, you would take the arc length traveled, divide it by the radius of the object's rotation, and you would get a value. That value might be 1, it might be 1.5, it might be 6. It's dimensionless because this is a ratio. This is meters over meters. And so instead of saying dimensionless, we say radians. So 1 radian is what theta equals when L and R are the same value. So when L equals R, then L divided by R will equal 1, and that's 1 radian. We can rewrite this in terms of arc length because sometimes we might be interested in arc length. Arc length is given by the radius times the amount in radians. And if you're going back and forth between two different values, what you know is that if L over R equals theta, and you go all the way around a circle, you have covered 360 degrees. If you go all the way around a circle, you've covered a circumference. A circumference is L equals 2 pi R. And radius is R. So L over R is 2 pi. So when you've completed one complete rotation around a circle, you've covered 360 degrees. Therefore, 360 degree is 2 pi radians. And so that's how you're going to get back and forth. So 1 radian would be 360 degrees, which is also 2 pi. 360 is to 2 pi, so that means that 1 radian is 57.3 degrees. 1 complete revolution around a circle is 360 degrees, is 2 pi radians. So let's take a look at how we can do a little bit of calculation with this value. The first example that we're going to take a look at is we're going to look at a bike wheel. And so this is just taking a look at how radians work. A bike wheel completes 4.5 revolutions, and we want to know how many radians that is. Well, this bike wheel with point P and radius R did 4.5 revolutions. So it went once, twice, 3 times, 4 times, and then it did another half rotation so that the point P ended up there. So it went around the circle 4.5 times. So what we want to look at is we know that 1 revolution is equal to 360 degrees is equal to 2 pi radians. So if you have 4.5 revolutions, and you know that 1 revolution equals 2 pi radians, so that's 1 revolution is 2 pi radians. So that means that 4.5 revolutions is actually going to be equal to 4.5 times 2 is 9 pi radians. Or if we wanted to put that in decimal form, it would be 28.3 radians. So 4.5 revolutions gives us 28.3 radians. It's just an easy way to talk about how an object turns in a circle, because theta is a really great way to measure how many times an object has traveled around an axis. So why is that useful to us? Well, let's take a look. Here I want to introduce you to our friend, the hawk. If you don't know, it turns out that birds have incredibly amazing eyesight. In fact, all birds of prey, so all of your hawks, all your falcons, all of your eagles, they're all day hunters. And they're all day hunters because they use their eyesight to find their prey. And it just so happens that we can determine a bird of prey's measurement because the line of sight of a bird allows them to see very small objects. So the higher up they are, we'll call that height a radius. The smaller, the larger the radius. And so the ratio for a very small animal, the length compared to the radius for a bird's eyesight in terms of arc length, is actually getting smaller. So the higher up a bird goes, the harder it's going to be, or the smaller the degrees that they're going to be able to see. And so we call this the arc length, and the arc length in the chord, which is the actual tangent line to the 2 points, is going to be very similar. So a certain type of bird of prey can distinguish an object. So we'll say that this is a red-tailed hawk, and we'll say that the bird can distinguish objects to an accuracy of 3 times 10 to the negative 4th radians. So the first thing we want to look at is, what is that number in degrees? Because you're a little bit more familiar with degrees, and you know that 360 degrees equals 2 pi radians. So if I wanted to change 3.4 times 10 to the negative 4th radians, 3 times 10 to the negative 4th radians into degrees, I'd have to divide that by 2 pi radians to turn it into 360 degrees. And if I do that, the radians will cancel out. Remember, that's an imaginary unit that we've created. And this is an incredibly small angle. It's 0.017 degree. So that's how small of a measurement the bird can see. Now, if the bird is 100 meters up in the air, that's incredibly high, we want to know how small of an object can the bird see. Can a bird see a teeny tiny little mouse? And so what we're going to do is we're going to say if theta equals L over R, we want to know how small the smallest L the bird can see when it's 100 meters up is. So we rearrange the equation, L equals R theta, and if we know the bird's eyesight arc, and we know how high up the bird is, we should be able to determine the approximate length of the object that he wants to be able to eat. Like, we want to be able to say, well, how small can it be and he can still eat it? So we've got 3.4 or 3 times 10 to the negative 4th radians times a radius of 100 meters, and that means that this bird can actually see an object that is 3 times 10 to the negative 2 meters long. If I want to put that in familiar units, that's the exact same thing as 3 centimeters long. A 3 centimeter long object is about like that. So that's like baby mouse size. So these birds have actually truly excellent eyesight. If instead of giving this value in radians, we'd been given the value in degrees, we would have had to convert it into radians before we could plug it into this equation to get such a simple answer. So radians are really simple for figuring out ratios between the radius and the arc length that an object sweeps through. So So let's go ahead and let's talk about some angular quantities. Angular quantities are basically the exact same thing that our translational quantities are, only now we're talking about quantities for an object rotating in a circle. So we're focusing on that motion around a circle. And so there's some really simple ones that we're going to take a look at. The first one that we're going to take a look at is position. So position, instead of talking about position in terms of x, for angular motion we talk about position in terms of radians. So if we wanted to talk about displacement, we would be talking about the change in the angle in radians. So that'd be your final position in radians minus your initial position in radians, and that would be displacement. And the units that we give it, remember it's more or less unitless, but we call it a radian. All right, and that's really convenient because looking at an object with rotational motion, right? If this is theta 1 and this is theta 2, then the change in position would be the change from here to here, and so it would be, if this is theta 1 and this is theta 2, the change in position would be from here to here. So this is your delta theta. So an object that moves from this position all the way to this position would have a displacement of this much. So instead of using x for displacement, or delta x, we use theta. Now in terms of velocity, there is a velocity. Velocity is displacement over time. So displacement over time for angular motion, we give velocity the symbol w, which I believe is lowercase omega. And what we do is we say that velocity is displacement over time, so our angular displacement is delta theta. So delta theta over time would be our angular velocity. And since displacement is in radians, angular velocity will be in radians per second. And this is for average velocity. If you wanted to find instantaneous velocity, you'd have to go over smaller and smaller time. So that means that instantaneous velocity would be equal to delta theta over delta t when t is becoming close to 0 or almost 0, and that would be your instantaneous velocity. Likewise, you've got the term alpha for angular acceleration. For linear acceleration, it's change in velocity over time. So for angular acceleration, it's going to be change in angular velocity over time. So the change from final angular velocity from initial angular velocity divided by time. So change in angular velocity over time will give us our acceleration. Likewise, instantaneous acceleration would be change in velocity over time as time becomes a smaller and smaller value. And our units are radians per second squared. So now that we've established that these are our angular quantities, angular displacement, angular velocity, angular acceleration, delta theta, omega, alpha, now we could say that here's a neat thing. If you've got an object and it's rotating, right, no matter what point you're looking at, whether you're looking at the green point or the black point, they're both covering the same theta in the same amount of time. If we were going to measure from 0 degree up to 90 degree, both points cover the exact same arc length in that same exact time interval. Likewise, if we're accelerating, we're speeding the rotation up, they would both speed up and cover that position or with the same change in velocity. So that means that for angular motion, the points are the same for every point on the object, whether we're hanging out all the way here out at the far point or whether we're hanging out right next to the axis. And that's really an interesting topic because you see That means that for every single point in an object, every single point is going to have the exact same velocity and the exact same acceleration when we talk about angular terms. Omega and alpha will be the same for every single point on the object. However, these points would also have tangential values, right? So a point right here would have a tangential velocity, right? If there were no force, if that point suddenly were to become detached from the other points on the object, it would follow a tangential path, and it would have a tangential acceleration. Another point in would likewise have a tangential velocity, and it would follow its own tangential path. And the tangential velocity for two different points is not necessarily the same as the tangential as the angular velocity, and they're not going to necessarily be the same amounts. So let's think about this. If we're going to calculate tangential velocity, it would be the change in position over time. That would be our tangential velocity. So L, which is just the length or pathway in a linear direction, L over T, delta L over T, would give us our linear tangential velocity. So remember that we have this value that we say that the arc length is proportionate to theta times the radius. If we plug that in for the arc length here, then we would get that velocity would equal the change in theta times the radius over the change in time. And if I pulled the radius out from the fraction there, then this change in theta over time is actually equal to angular velocity. So that means that I can have the equation velocity equals radius times angular velocity. Velocity equals radius times angular velocity. That's the relationship between velocity in the tangential direction and velocity when we talk about rotational velocity. Remember that the angular velocity is the same for every single point, but the velocity isn't necessarily. The velocity increases as the radius increases, because if this value is the same, we'll give it the value 5. And you've got a point close to the center. That point close to the center is going to travel a smaller path length as it travels around the circle, compared to this point with a larger radius actually covers a larger displacement comparatively. So here, if we've got this point right here covers this displacement here with a tangential velocity as such, and it covers delta theta in that time with an angular velocity of w. So that means that that velocity will be equal to r omega. If we look at the two different objects, or two different points, they both have tangential velocity, right? They both cover the exact same theta, whether it covers it here or whether it covers it here. The theta is the same. The difference is the ratio between L and R. Here's a short L. Here's a short L for a short r. Here's a long L for a long r. So that ratio keeps theta the same. However, and it keeps omega the same. However, it's going to change this value because the radius is shorter for RA and longer for RB, which means that this object A, had to cover a shorter linear distance than this point right here, had to cover a longer linear distance in the same theta. So while the angular velocity and the angular displacement is the same, the tangential velocity is much bigger for points further away from the point of rotation. So with that concept, let's go ahead and go over this concept example, which is the lion and the horse. So there's a rotating carousel that's rotating around a center, an axis of rotation. One child is sitting on a horse near the outer edge, and the other child is sitting on a lion on the inside of the circle. So which child has a greater velocity for tangential velocity, and which child has a greater angular velocity? So let's consider. We'll say that this is our starting position. And if they rotate around the same amount and have this be their final position, then their delta theta will be this. This is their delta theta. So their delta theta is the same, whether it's this child or this child. And they'll do that in the exact same amount of time. So that means that their angular velocity is going to be the same. Their theta is also the same. But here, this child has a small radius and this child has a larger radius. This child covers a much larger path length than this child. Therefore, the horse would be given by the angular velocity, which is the same for both of them, times the radius of the horse, which is a larger value. And the lion would be given by the angular velocity, which is the same for both, and then the lion's radius. This value, the velocity, is much larger. So the child on the outside is actually moving with a larger tangential velocity, even though their angular velocity is exactly the same because they covered the exact same angle in the time that they were traveling. So let's go ahead and let's look at linear acceleration. To look at linear acceleration is slightly more complex. And in order to do so, remember, we're going to have to look at the fact of the relationship that velocity equals radius times angular velocity. Now, just like an object would have a tangential velocity, it can have a tangential acceleration. A tangential acceleration would be how it's speeding up tangent to its rotational pathway. So an object can speed up. Let me get those lights. If an object can speed up, it can have a tangential velocity. Tangential velocity is given by change in velocity over change in time. And our tangential velocity is going to be equal to r delta w. So if we plug that in, then we get r delta w over t. Delta w over t, change in velocity over time, is this value right here is our angular acceleration. Therefore, tangential acceleration is given by r alpha. That value tells us how an object is speeding up in the tangential direction. But remember, the objects moving in a circle also have an acceleration that changes their direction. And that acceleration is a radial acceleration or centripetal acceleration. And you know that centripetal acceleration is an important part of an object that moves in a circular pathway. And that's given by v squared over r. Now, we know that v is r omega, so let's plug in r omega, radius times angular velocity, square it, and you end up getting omega squared, r squared divided by r squared divided by r is r. So radial acceleration is given by omega squared over times r. So now we've got acceleration for an object that's changing its directions constantly, which all rotating objects will have that, and tangential acceleration, or how that object's speed is changing in the tangential direction. So now we could find the total acceleration. The linear acceleration is always going to be a total of those two components. It will only equal one or the other if there's no, for an object rotating, it cannot ever just equal tangential acceleration. But if there is no tangential acceleration, it could equal the radial acceleration. So to find the total, we're going to have to sum up the tangential and radial acceleration. But remember, this is vector addition here, because tangential acceleration is tangent to the pathway, and radial acceleration always points toward the center of the circle. They're always at a 90-degree angle to each other, so the actual total will be a vector addition. Vector addition means that the total is going to equal Pythagorean's theorem, tangent squared plus radial squared, square root of those. So remember that vector addition is actually going to be really important. I have a toothpick in here, it's bugging me. Okay, so let's go ahead and let's summarize our values. Which means I have to zoom out. Okay, so in linear terms, we have displacement, velocity, and acceleration. And in linear terms, we say tangential acceleration in the same direction as velocity. All right. For rotation, you've got displacement, theta, rotation, omega, and acceleration alpha. They each have a relationship. You can go back and forth or convert those values. Displacement is L equals radius times displacement. Velocity equals r omega, and acceleration is r alpha. There's one more that we could add in here, and that is our centripetal radial acceleration. Which would still be related to our rotational acceleration, and the relationship there is omega squared times r. So let's go ahead and let's look at an example of how to do problem solving with this. Okay? So here we're going to be looking at when you have a combination of angular and linear velocities and accelerations. You've got a carousel that starts at rest, and it experiences a constant angular acceleration of 0.060 radians per second squared, which causes its angular velocity to increase from rest for 8 seconds. At the time 8 seconds, we're going to find the angular velocity. We're going to find the tangential velocity of a child who's 2.5 meters from the axis of rotation. We're going to find the tangential acceleration for that child, the radial, the rotational or centripetal acceleration, and the total acceleration for that child. So here we go. Here's the carousel. Here's a radius of 2.5 meters. Here's the child right there that we're talking about. Child loads up onto the carousel. Carousel starts to speed up. It continues to speed up for 8 seconds, and then it has a constant velocity. So if we're going to first find the rotational velocity for that object after 8 seconds, we know that the average acceleration was 0.060 radians per second squared, and that's going to be the final velocity minus the initial angular velocity divided by the change in time. Well, it started from rest, so our initial angular velocity is 0. Our time is 8 seconds, and our acceleration is 0.060 radians per second squared. So 0.060 radians per second squared times 8 seconds will give us our final velocity, angular rotational velocity, which was 0.48 radians per second. Now that we have that and we have a radius, we can find the tangential velocity. Tangential velocity, remember, is tangent to the circle, and that's given by r omega. Our radius is 2.5 meters. Our rotational velocity is 0.48 radians per second. So our actual tangential velocity is 1.2 meters per second. Now we can find tangential acceleration. Tangential acceleration is given by alpha r. We know that the rotational acceleration is 0.060 radians per second squared. Times that by a radius of 2.5 meters, and you've got 0.15 meters per second squared. That's our tangential acceleration. Now we can go further to find our radial acceleration or centripetal acceleration, which is v squared over r, or we could either do v squared over r, or we could do omega squared times r. I'm going to do v squared over r because I have 1.2 meters per second. I'm going to square that and divide it by a radius of 2.5 meters, and we end up with a centripetal acceleration of 0.58 meters per second. Now remember, the total acceleration is the acceleration tangentially that caused the horse to speed up, and the acceleration radially or centripetally that caused the object to move in a circle. So the total is going to be the vector addition of those two at a 90-degree angle, or tangent squared plus centripetal squared. So that's going to be 0.58 squared plus 0.15 squared. Square root both of those, and you end up getting 0.060 meters per second squared. That would be the total acceleration, but acceleration is a vector. You know that it's going to be some value in between them, so we need to know the angle. If they're in there and we want to know the angle, it's going to be opposite over adjacent, so it's going to be tangential. The tangent of those two values is going to be opposite over adjacent, so tangential over radial. So you take the inverse tangent of 0.15 over 0.58, and you're going to get 0.25 radians, or approximately 15 degrees. One of the things to notice is the total acceleration is 0.060 meters per second squared, and your radial acceleration was 0.58 meters per second squared. And your tangential acceleration was only 0.15 meters per second squared. So that means that your total acceleration is mostly centripetal. There's only a little bit of tangential acceleration that actually causes the horse to speed up. So we're going to take a look at some important relationships. We're going to be revisiting the concept of frequency and period. So for frequency and period, let's remember first that frequency is the number of revolutions per second that anything can take. So 1 revolution per second would be a frequency. 10 revolutions per second would be a frequency. Notice that revolutions is a unitless concept. It's how many there are, and seconds are on the bottom. So if we were going to do this in terms of radians, we could say that 1 revolution per second, 1 revolution would be all the way around a circle, the entire circumference. So that would be 2 pi radians per second. Frequency is therefore given by the angular velocity divided by 2 pi, which means that the angular velocity could be calculated by multiplying 2 pi times the frequency. The unit for frequency is a hertz. That's 1 revolution per second, where revolution is a unitless concept, and frequency is the inverse of period. The period is how many seconds does it take to complete 1 revolution. These are both review terms from our centripetal motion and centripetal forces unit. So let's go ahead and let's apply them. If you've got a hard drive platter that can rotate at 7,200 revolutions per minute, RPM, we can figure out what the angular velocity of the platter is. So, revolutions per minute, 7,200 revolutions per minute. Well, first thing I know, I'm going to need to turn that into seconds. And then I need to turn revolutions into radians. 1 revolution is 2 pi rad. So revolutions cancel, minutes cancel, and then we're going to get radians per second. Radians per second is actually, so radians per second is therefore 754. So now it says, if a reading head on the drive is located 3 centimeters from the rotation of axis, so you've got this, you know that W equals 754 radians per second. So now if you've got something 3 centimeters away from that center of rotation, axis of rotation, we should be able to determine the linear speed. Linear speed is given by omega r. So we can take that 754 radians per second and times it by 0.03 meters, and we'd get a tangential velocity of 22.6 meters per second. Now, the last thing that we can determine is if a single bit requires 0.5 micrometers of length along the direction of motion, we can figure out how many bits per second the writing head can write if it's 3 centimeters from the axis. And so you might be saying, what? Well, here's the thing. If the writing head can do 0.5 micrometers, that's 0.5 times 10 to the 6th meters per second. That's, how many meters? Now, we also know that 0.5 times 10 to the 6th meters that the object can record is happening at 22.6 meters per second. So that 22.6 meters per second can be multiplied by 5 times 10 to the negative 6 meters per bit. And those meters will cancel, and you'll end up with 4.5 times 10 to the 6th bits per second. So that means that that writing head can write at 45 times 10 to the 6th bits per second, or that's 45 megabits per second. So that gives us a really good idea of how a frequency, how many revolutions per unit of time, could be used to solve for all sorts of angular quantities.